Okay, good afternoon. Um, these here are some of the ground rules that Lindsay just went over, so we're all set there. Just a reminder that you will get your certificate, but it may take a few days for that to come out. Some of the topics we're going to talk about today are what goes into designing a subsurface investigation program, the different subsurface investigation methodologies that we have out there. We'll talk about what goes into reviewing boring logs or subsurface investigation and CPT logs. We'll also talk about different soil classification systems and engineering properties of the soil. And then we'll get into a little bit of geotech evaluations at the end. So the biggest thing when we go into determining the number of soil borings is making sure we look at what codes that we're going to be using. When we look at the New York State Building Code, there is no requirement for the number of borings. The number of borings should be determined by the geotech engineer of record. And that generally, as a rule of thumb, we use one boring for every 2,500 to 5,000 square feet of building footprint. Larger buildings such as big box warehouses, big box retail, we can generally stretch that out to one boring for every 10,000 to even maybe 20,000 square feet, depending on the project and project location, the types of soils that we think we're going to be in, and also the size of the building. The other thing that goes into this, sometimes certain companies have specific requirements for the number of borings that we need to do, and we need to look at those as well. When we talk about projects other than buildings, we have to look at the different requirements for those projects. Bridges, generally we need at least one boring per abutment. If there's going to be a planned center pier, we would want to do borings for that as well. New York State DOT a lot of times actually wants 4 borings, 2 per abutment on the ends. So that's one thing we have to look at. Retaining walls, a lot of times that depends on the length of the length of the wall and how tall the wall is. Roads and roads, parking lots, pavements. It depends on how big of a project it is, how long the road is, how big the parking lot is. So that's one that if you're going to be looking at those types of projects, you want to get in touch with your geotech engineer and start discussing as to how much they think is going to be needed. Same with stormwater areas and solar fields. The stormwater areas, a lot of times, it's dictated by the New York State DEC design manual. But again, those are pretty stringent requirements, and a lot of times they end up getting stretched out a little bit further. The next part, after we figure out how many borings we need to do, we need to figure out how deep we need to drill. The building code does not require a 100-foot deep boring, although it does require us to know the soil properties in the top 100 feet. But that we can use our knowledge of the soils in the area, along with our experience and our and other factors, if we have projects that are nearby that tell us certain things, and also our knowledge of geology. So if we encounter very compact soils at say 20 or 25 feet, we know they're not going to get softer below that. We can use that knowledge to terminate those borings well short of 100 feet. To determine the seismic site classification, we need to know the soil properties, which is either the shear wave velocity, standard penetration resistance, or the soil undrained shear strength. Now, I will caution you, when New York State adopts the newer version of the IBC, some of this may change because they're switching to more of a shear wave velocity method versus using a standard penetration resistance. And we haven't quite figured out exactly how all that's going to shake out yet, as we're not quite there yet. Once we know what the soil properties are in the top 100 feet, We determine the seismic site classification, which are A through F, and then we can obtain the spectral response numbers. Those are generally obtained from various websites that are available based on the project coordinates or location. These make sure, though, when you're doing this, that you don't confuse the seismic site classification with the seismic design categories, which are also A through F. New York State is going to typically fall into site classifications B, C, and D, where B is bedrock at a shallow depth, and D is, I think they consider it, medium compact soils. Some exceptions in New York State are the Onondaga Lake region, which has very deep bedrock and/or glacial till in excess of 300 feet. There's also some loose sands in the Albany area, and then you get into some of the river and stream valleys where that doesn't always hold true as well. So we have question number 1 here.
Back to you, Adam.
Okay, so the first question, true or false? A 100-foot deep boring needs to be drilled to determine the seismic site classification. The answer for that is false. So now that we've determined the number of borings or boring or test locations that need to be done, we've also talked about the number of the depth that we need to get them to. Now we're going to talk about the different methodologies that we have to obtain that subsurface investigation information. Most commonly is conventional soil borings. Cone penetration testing is another method, and then we'll talk a little bit about geoprobe and test pit methods as well. While I've got everybody on this screen here, that picture of a drill rig right there, that's a CME 850X. That is a track-mounted drill rig. And when people refer to an ATV drill rig, a lot of times that's one of the options that we're referring to. When we refer to an ATV rig, we're not talking about a four-wheeler or even a side-by-side. We're talking about something that's generally track-mounted and can go many more places. That drill rig has a ground pressure when it's moving on the tracks of less than people walking so we can go into swamps and through deep snow and such. Conventional drilling, advancing the borings is either done with a hollow stem auger, which is, we'll talk about it here in a little bit, or flush joint casing. We have different sampling methods as well, taking split spoon samples, undisturbed samples, and bedrock coring. This is also a good example of picture here. This is one of our smaller geoprobe ATV rigs that is mounted on a rubber tracked carrier. That carrier is similar to like a mini excavator, and while it can't go probably everywhere that CME 850X can, it can go a lot of places because it's fairly low ground pressure. Hollow stem augers. The picture in there shows a picture of some sitting on a pallet. What it is it's a center sampling tube that has auger flights around it. And as we link them up, they're in 5-foot sections. We advance those down to various depths, and we determine that we obtain the samples at those various depths. The size of the size refers to the diameter of the center sampling tube, not the outside diameter. Your common sizes are 3 1/4 and 4 1/4 augers, which drill holes probably. The 3 1/4 drills about a 6-inch hole, and the 4 1/4 drills about an 8 or a 9-inch hole, depending on the brand of auger. Some advantages of them: they're relatively quick. It's not uncommon to advance 60 to 70 feet of boring with hollow stem augers a day, which makes them economical. Also, another key is water is generally not necessary, which is a good thing when we're working in the wintertime where drilling with water is hard. Oh, I got to go back one slide here. One thing you're limited to with the hollow stem augers is total depth. Generally, we don't try to drill deeper than about 100 feet with the hollow stem augers. So now we're ready for question number 2. How deep can you drill with hollow stem augers?
Back to you.
Okay, the answer for that question we just talked about was 100 feet. The reason they're limited to about 100 feet in depth is with those 5-foot lengths, they're linked together by a bolted and keyed connection. And if you link more than about 20 of those connections together, they tend to get a little bit flexible. The other method that we can use that's commonly used to advance borings, other than the hollow stem augers, is flush joint casing. Flush joint casing can be either driven or spun into the ground. The real advantages of the flush joint casing is the quality of the borehole that it produces. It's very straight. We can get to depths of at least 300 feet. You also have the ability to advance through um, cobbles and boulders that you can't necessarily get through with the augers. This here is a picture where we're advancing casing. If you see at the bottom of the, right at the ground level, you'll see a white plastic tee, that's PVC tee that's sticking on top of it. And what that's doing is it's directing the water away from where the guys are standing. The disadvantage of using flush joint casing is you have to use water. There's no way around it. It's either being used to advance the casing itself, or it's being used to, when we flush out the inside with the tricone roller bit. So it becomes a little bit more difficult as it gets colder. We do drill all winter long, and we can drill with casing all winter long. It's just that the guys have to be a little bit more cautious, and it generally takes a little bit longer, and it has to be a little bit more conscientious of how they're handling things. An idea of the amount of water you need is generally, I would say, between 100 and 200 gallons per 5 feet of advancement, but that's also not saying we can reuse some of that water. That tee can be hooked up to the tub, and we can recirculate water at times. What you don't see in this picture here is that there was a large 2,000 gallon water tank truck just off to the side. So that's why they weren't worried about reusing that water. So whether we're using hollow stem augers or flush joint casing to advance the borings, generally we use, our samples are taken with a split spoon sampler. Split spoon sampling is done in accordance with ASTM D1586. And we drive a 2 or a 3-inch split spoon with the 140-pound hammer, and it falls 30 inches. Generally now, it's almost always done with an automatic trip hammer, which is probably for about the last, I would say 15 years or so. Most rigs have that on it. And what that does is it adds to the consistency. Before that automatic trip hammer, what we were using was a cat-headed rope, where the driller would pull a gin line rope and would lift the safety hammer up 30 inches and then let it drop. They're not quite as efficient in energy transfer as the automatic trip hammers. Safety hammer, I think, transfers somewhere around, depending on the driller, 60% of the energy, where an automatic trip hammer, most of them are in the 85 to 90% range. After the split spoon sample is taken, we bring the sample up to the top, and it's classified in the field, and it's also a portion of it's put into a glass jar and returned to the lab for future lab testing and classification. Undisturbed samples are taken in fine grained silts and cohesive clays. It has to be a cohesive material for this to work. What you see in the picture there is the extraction machine that takes the sample out of the tube in the lab. And if you look at the shinier piece of metal there, that is where the tube is. And what you see on the end is actually the plunger that pushes it through. So the sample's already been taken out of that tube at this point. When we advance a undisturbed sample, you're advancing it with either the hydraulic pressure of the drill rig or water pressure activated through the water pump to push it into the ground at a slow, steady speed. After we extract the sample from the ground, the tubes are sealed with wax on the top and bottom to maintain the moisture condition, and they're returned to the laboratory, and we can do a lot of different testing on them. Some of the most common things that we do on them are consolidation tests, triaxial compression. We can do permeability testing on the soils, and they provide the most accurate representation of the in-situ conditions that we can get. But again, a disadvantage is if it's not a cohesive material, if we tried to push this into sand, essentially we would come out with an empty tube because there's nothing to hold it in there. Question number 3. In what type of soil condition is a Shelby tube most conducive?
Back to you.
Okay. The Shelby tube the answer is B, soft clays. It won't work in loose sands like I described. It also won't work in bedrock or glacial till because as you're pushing the tube, you just won't be able to push it into those materials. When we go to obtain samples of the bedrock, which we can do, we core it in accordance with ASTM D2113, and that's using a double tube core barrel with a diamond cutting shoe. The double tube core barrel, what the outer barrel is has the cutting shoe on it, and that is spinning at a high rate of speed. And the inner barrel, which is where the sample actually rides, is on a bearing system so that theoretically it's not spinning and protects the sample inside that high speed cutting barrel. The samples are returned to the laboratory and we generally determine the RQD, and we can do laboratory testing such as compressive strength, and there are some other lab tests that can be done depending on the type of projects. Here's some pictures where we are drilling in a rock quarry. This is for the expansion of the rock quarry. They needed samples taken. This also gives you an idea of what our truck-mounted drill rigs look like. Again, when we talk about a truck-mounted drill rig, we're talking about something that's a tandem axle truck. We do have 1 or 2 single axle trucks as well, but they're large, they're heavy, they're similar to the weight of a loaded tandem axle dump truck. So it's not like it's a 4-wheel drive pickup truck and where they can go. And that's why we have a lot of the ATV rigs that we have that have better availability to move and off-road conditions. Cone penetration testing is something that I think is going to become more popular with the advent of the new seismic requirements in the upcoming building codes. What you have is you have an electronic cone, which is that silver object on the bottom of the picture, that's pushed into the ground, and up at the top, we're recording the tip resistance, the side friction, the pore water pressure, and also the shear wave velocity is recorded at various intervals. So if you look at that cone that's at the bottom of the picture there, the tip resistance is measured on the conical tip. The side friction is measured on the 6 inches of material of stainless steel that's just above the tip. The pore water pressure is measured through a special porous element between the tip and the sleeve. And then just above where that friction sleeve is, where the color changes a little bit, is where there's a seismic geophone. And to measure the seismic shear wave velocity, what we do is we, at various intervals, generally 1 meter or 2 meters, we stop the push, and underneath the back jacks of the drill rig, there's a steel I-beam that we hit with the sledgehammer on either end to create a shear wave into the soil. Because we know how deep in the ground the cone is and that geophone is, when we hit the steel I-beam, we start a timer, and then we can see the wave arrive at that geophone. So therefore, we can calculate the shear wave velocity. Some advantages of cone penetration testing are it's fast. I mentioned with hollow stem augers, 60 to 70 feet a day. Sometimes you can get around 100 feet. I didn't really mention it for the flush joint casing, but we've had certain project sites where getting 20 feet a day is really good. Other project sites where getting 100 feet is possible. That's highly dependent on where the water is, how hard the soils are, and such. But when we talk about cone penetration testing, advancing 200 to 400 feet of cone pushes a day is not out of the question. So we can get a lot more production, test a lot more locations in a shorter period of time, making it more economical. Because we determine that seismic shear wave velocity, we can accurately determine the seismic site classification. The data that we also get is very good for driven pile design in soft or loose soils. It's also very useful and cohesive in sand soils because some of the cohesive soils, when we take split spoon samples, the soils are so soft we don't get a lot of data because the blow counts, it just doesn't resist the split spoon very much. Disadvantages of cone penetration testing are you're not able to advance it into very dense soils or bedrock. There's also no sample collected. I'm a geotechnical engineer, and I like to go down in the laboratory and play with samples. A lot of times people ask me what I do for a living, and one of the things I say is I sometimes make mud pies and get paid for it. I want to be able to touch that sample and play with it and hold on to it. And because I can't with this cone penetration testing, that's a big disadvantage. Generally, when we do cone penetration testing, it's not the only method we use on a site. We'll generally combine cone penetration testing with conventional borings so we can get those samples and see what's actually there so that we make sure we get the client the best product that we can. Another disadvantage is it requires a large drill rig for reaction weight. Generally, we're using like that tandem axle truck drill rig or the CME 850X. We have used our GeoProbe rigs a few times to push it, but we're limited in the amount of depth that we can get, but for certain projects it may work. So here's a typical CPT log. If you notice, you've got the different graphs. You have the graph of the tip resistance, the graph of the friction sleeve. The next graph over is a graph, it's a ratio between the friction sleeve and the tip resistance that's calculated. The fourth graph over is the pore pressure. The fifth graph over is an estimation of the SPT end values based on the previous four graphs. So what they do is they've done all kinds of correlations over the years, and they say that if your tip resistance and your friction sleeve are this, your pore pressure is this, the SPT value should be about this. It's also how the soil behavior type is determined. If you look at the colors in that graph and you look at, there's a key at the bottom that shows you what those are. Again, that's not saying what the soil is, it's saying what it behaves like based on the data that we determined from the cone. Here's a picture of doing some cone penetration testing on a barge. If you notice, the way we get that data up to the surface, if you see in between the rods that are laying on that rack, there's a blue cable. That blue cable is hooked to the top of the cone where Aaron's in the process of screwing that onto the rods. And it's also hooked to the computer on the other end, which is just off the edge of those pictures. And when we drop that down in, when we're doing work on a barge, we always put casing down through the water column to help support the rods as they go down, to make sure that they stay straight and to give it some additional resistance when we're or some resistance to buckling when we push. Okay, question number 4. What type of soil parameters does CPT testing determine that conventional? The question was supposed to be what type of soils is it conducive to use, and the answer was all of the above. But I think there was a change in our presentation at one point because that used to be the old question. So another method that we have to get subsurface information is using our small geoprobe that's mounted on a 4-wheel drive truck. Now this is different from the geoprobe that I showed you before, which is more of a conventional drill rig. This unit here that you're seeing in this picture is a direct push only unit. So it obtains a macro core sample by using hydraulic downfeed pressure from that rig, and also a hydraulic hammer that acts like a jackhammer to advance the sampler. The sampler that's advanced is called a macro core, which is similar in size to a split spoon, although they're 4 or 5 feet long, and they also have a Lexing plastic liner that goes inside the sampler instead of splitting in half like a split spoon. I think if you drove something like a split spoon with this, it would destroy it because it would split apart with the force that it puts on it. So that's why they use a plastic liner to get the sample out. This type of piece of equipment was originally developed for the environmental field. They used it a lot when it first came out for all the mom and pop gas stations that had leaky tanks and leaky pipes. And then eventually we got a hold of this as geotech engineers and we found other uses for it. Common is doing soil classification projects. If we don't really care about the blow counts, maybe it's a water line and all they want to know is what the soils are so that they can provide that to the contractor so the contractor knows what they're digging in. Another option is to do bedrock profiling with it. It's pretty quick to do a whole bunch of probes that are, say, between 6 and 10 feet, where doing it with a conventional drill rig wouldn't be economical. The other option is to do it where we want to get good groundwater elevations. We can set small temporary wells with this unit relatively quick and easy, and then we can get good groundwater data, and we can monitor groundwater data over a period of time if we need to as well for seasonal fluctuations. Whoop, I went past test pits. Test pits are a really good tool for certain sites. Test pits are great if we start encountering fill on a project site. They're really good for groundwater investigations, for shallow groundwater levels, to see how hard a project site might be to dig in. They're really good for collecting bulk samples, which is something we seem to do a lot more of now. We get a lot of the power projects and or solar projects where we need to collect bulk samples for thermal resistivity testing. Test pits is a good way to do that. Some disadvantages of the test pits is you're limited in depth. Generally, when we're digging test pits, we're using some form of a mini excavator or a small backhoe, and you're limited to between 8 and 12 feet with those units. if you want to dig a hole much over that 12-foot depth, the machine that you have to get there is so large it then becomes cost prohibitive to get it there. The other thing is because we don't have any of the data that we need to determine the seismic site classification, it's really not useful, and we can't really determine the site classification with the test pits, unless the only way we could is if we hit bedrock within the test pit. So subsurface investigation logs, more commonly referred to as boring logs. The wealth of information that they can contain is really high. There's a lot of things on there that a lot of people don't realize if they start looking at them. You have the different soil types, the soil consistency, groundwater information. There's a lot of notes about what might be happening as well. I know these are a little bit hard to see because they're small, but if you look at these on the screen there, you have up near the top, you have a lot of project information, what the project was for, what the name of the project was, information about where the boring might have been. You also have information about the groundwater depth at various times and dates. You have information about how the boring was advanced. This one was advanced using a 3 1/4 hollow stem auger. And then you get into kind of the meat of the information. You have the blow counts that were obtained by driving the split spoon sample on the left side there, and on the right side you have the soil classification of those samples. These here are all have Burmeister soil classification on them, which is what we generally use. We do use some other systems at times, but that's generally what we produce our logs in, is Burmeister. So that's page 1 of a log. This here is page 2. If you notice, at about, I think that's about 30 feet, the soils get quite a bit denser, and the soil classification changes from a kind of a loose sand or clay into more of a glacial till type material with a sand, dense sand and gravel. This next boring log sheet I have in here to show, you can see where we took Shelby tube samples in this one. Shows you what those symbols look like and shows you the depths. Those samples for this particular project, we did do different consolidation tests on, so that we could determine the settlement for the projected building that was going to be on this site. Because of those tests, we ended up moving the building on the site to an area where we got out of that soft clay and into a better sand and gravel material on the backside. This here is a different boring log here. This shows you what a rock core would look like. It shows you how it's classified. We have both the recovery, we have the number of pieces, and a piece is a full wafer thickness or full wafer diameter of the core. And then we also record the RQD, which the RQD is the total length of all the pieces that are longer than 4 inches divided by the total length of the run. And it's presented as a percentage. For this project here, this rock core was 0, but that's not, and it's more of a phylite is similar to a shale if somebody's not familiar with that. Different soil classification systems that are used in the geotechnical engineering world. Your 2 most common are your Burmeister and your unified soil classification system. New York State DOT does have their own system, although I think they've gotten away from that a little bit, and they're using more of a unified system now. There's the USDA soil classification system that's used a lot of times in the agricultural world for that, but it is something that is used, and sometimes we do get asked to classify soils in that way. We're going to talk here a little bit more about the Burmeister and the unified system, but not the other two. Burmeister soil classification is a visual manual procedure. The drillers do it in the field, and it's also verified in the laboratory by a soils technician or engineer. When I say visual manual, I say it's one of those things where we take the soil sample, we dump it out on the table or on a piece of plastic, and we play with it. We separate out the gravel particles, we separate out the sand. We may take a portion of it and do what we call a wash, where we put water over it to get rid of the silt and the clay to determine how much, what the makeup of the soils is. And here's the classification. This is the particle size determination. Everything from boulders, which are particles greater than 12 inches, down to microscopic clay. And when we determine how much of these we're doing it in percentages by weight. And if you look back at the boring logs that we had, you'll see in the classifications words like some, little, and trace, and those all have meaning as to the, and I'll go back to that page here. If you look up at the top above the soil classification, you'll see where those are designated, what those words mean, and how they can help you determine how much of each is in the sample. Unified soil classification actually has two different ASTMs. 2487 is based on a laboratory analysis. So you have to do a laboratory sieve to do a classification in accordance with 2487. You also may have to do other tests such as the Atterberg limits, which we'll talk about in a little bit as well. D2488 is a visual manual procedure, and that's somewhat similar to the Burmeister, although the classifications are slightly different the way they're presented. This is a chart out of the unified soil classification system. One of the disadvantages of the unified system is you don't always know the percentages of some of the minor components without knowing the system inside and out. You can have a classification of silty gravel. If you have silty gravel, that doesn't mean you don't have any sand in between there. It just means that you have less sand than about 5% or 15%. So unless you really understand how that system works, it's very difficult to know exactly what you have for soils. That's one disadvantage, whereas the Burmeister would tell you, it might say trace sand or little sand. Unified doesn't, it leaves that part out. That's one disadvantage of it. Some different engineering properties of the soils that we can determine in the laboratory. The easiest and most common tests that we do on soil samples from a drilling job are the natural moisture content. You take a sample, dump it into a tare, which is a pan, put it into the oven, dry it out, and determine the natural moisture content. It gives a lot of information about how the sample is going to react, how the soils are going to react, how maybe where the groundwater level is. And again, it's the most simple test that we do. Atterberg limits determines the liquid limit, plastic limit, and plasticity index. Those are going to be done on clay soils, and they're going to tell you how the soil is going to react and how it's going to behave when we go out to do work with that material. Is it going to act like more of a liquid, or is it going to act more of like a plastic type material where a liquid material may flow, where a plastic material is going to move, but it's not going to flow like like a real soft material. The other tests that we can do are, we didn't list it on this sheet, but particle size analysis, which is a sieve, that can be done as well. We also, on undisturbed samples from Shelby tubes. We can do things such as the shear strength, internal friction angle, and consolidation potential of the soils. And these get into higher level analysis when we're trying to do slope stability or settlement of buildings on clay, where we need to know those soil parameters to be able to determine what might happen to with that project. So after we get all the field work done, get all the soil samples back to the lab, classify them, do all those lab tests, we can answer every structural engineer's favorite question, which is, what's the bearing capacity? There's a lot of things that go into determining the bearing capacity. Everything, we look at the whole of the project, you know, the information that was determined in the field, the types of soils, the different lab tests, and then we can look at different calculations and different tables and charts to get that bearing capacity. The other things that we can determine with a lot of these are lateral earth pressures. The lateral earth pressures are useful when designing basement or retaining walls. There's also some other uses for those. We can talk about slope stability, you know, for various projects, determining whether or not a certain slope might be stable during construction and/or during final project design. We can also talk about frost heave and where, you know, how deep foundations need to be founded so that they're not going to heave. Some other things that can be determined or that can be presented in the geotechnical report. Generally, when we do the geotechnical report, we start out with a site and project description. So if I'm writing a report for a project, I'm going to ask the architect or engineer, or maybe the project owner, I'm going to ask them questions about what they're doing. It changes a lot of recommendations. Are you building a 1 or 2 story building, or are you building a 10-story building? You know, it changes the loads. Are you building an office building, or are you building a parking garage? You know, those are things that we need to know so that we can provide the appropriate recommendations. Generally, there's a section in there that discusses what we did for field investigation, how we advanced the borings, the number of borings, the depths, what sampling methods were used. Then we get into a written description of what's on the boring logs and the groundwater information. And we try to generally write that so that the general public can understand it without too much trouble. There's generally a section on the laboratory testing that we've done, what the results are, maybe some interpretation of the results if needed. And then we can get into the meat of the report, which are the engineering findings and recommendations that are related to the design and construction of the project. You know, if it's a shallow building and there's I'm sorry, it's not a shallow building, a building founded on shallow foundations, you know, we'll provide recommendations as to how to prepare that footing subgrade, provide recommendations, you know, if we think stone or such is needed underneath them. We'll do a lot, you know, provide a lot of recommendations about groundwater control, you know, and how that should be done, or how difficult it may be. Also can provide recommendations for pavement design, you know, the thicknesses of the various layers, all sorts of different things can be done there. If it's a bridge project or a project founded on loose or soft soils, we may provide recommendations for deep foundations such as driven piles, helical piles, mini piles. There's all different kinds of alternative systems that we can look at as well. Sometimes there are things that are more economical that may save a project a lot of money. Other services that we can provide as geotechnical engineers are site visits during construction. This is one of the things that I really like about being able to do this. When I'm sitting here in my office, or even when I'm out with the drill rig, we're looking down a relatively small hole, taking a relatively small sample on possibly a big site. Doing visits during construction, I'm able to look at the entirety of the excavation and make sure that the recommendations that we provided are relevant for the entire site. There are times where certain things will come up in between where we did borings that may cause issues with the foundations. We want to know about those, and we like to be able to um, provide recommendations in the field, and we can do a lot of things on the fly that will help alleviate problems going down the road. Other things that we as geotech engineers get asked to do a lot are infiltration testing, which relates to the stormwater design. That is, again, becoming much more popular. There's been a lot more of that in the last few years. And resistivity testing has also become more prevalent with a lot of the power projects that we have, whether they be solar sites, electrical transmission lines, upgrades to substations. We've even done some resistivity testing at some battery storage facilities for the design of the grounding systems. So the last question is question number 5, which is true or false, determining the groundwater condition. So groundwater.
And back to you.
Okay, I didn't specifically give the answer to this one during the presentation, but I hope everybody figured this one out, that it was true. A long time ago, when I was giving this presentation, somebody approached me from one of the state agencies, and they said somewhere around 50% of all extras asked for on a construction project that they're involved with are related to groundwater. Whether it's a scenario where the contractor didn't understand what was in the geotech report, maybe there wasn't soil borings or geotech report done and they encountered something during construction, or maybe a project was drilled and designed during a dry time of the year and it was constructed during a wet time of the year and the conditions varied because of seasonal variations. So determining that groundwater table is extremely important. So with that being said, these are a couple more pictures of our truck mounted drill rigs. Like I said, we have some single axle units. That's also that double axle unit that is out in the water there. It's on a submerged road. With that, we want to thank you for your participation and remind you again that certificates will go out, but they may be a few days before they get out. And at this point, Lindsay, do we have any questions?
We have many questions.
Okay.
So I'm going to go through a handful here, and if we run out of time, we can email answers out to anyone else whose question we didn't get to. So the first one is, could the water change the characteristics of the soil samples, or does it not get into the actual sample tube? And this is from Paul.
Yes, the water can, when we take either a split spoon sample or a Shelby tube sample, we do recover the groundwater that's in the pores of the water, and that can affect the soils to some extent in the soil samples. We try to account for that and recover some of that water out of the tube when we actually put the sample in the jar.
All right, next question from Bob. Do you perform any mud rotary drilling?
Yes, mud rotary is similar to using casing and roller bit. I didn't specifically talk about it in here, but sometimes we even use mud with our casing, depending on the types of soils that we're drilling in.
All right, the next one was from Sam. For rock coring, does ASTM 6032 apply?
Yeah, I believe that might be the newer number, and that may be the case. I would have to double check that one.
All right, and from Maxwell, is there a piece of equipment similar to the penetration cone that could give us a better idea of the actual applied PSF during a bearing grade inspection?
Um, there are certain types of sample tools that we can use, like dynamic cone penetration testing, which is it's actually, I would say, more similar to doing a split spoon sample. It's a slide hammer that advances a point in the ground. We do use that sometimes to help verify bearing capacity, but it's limited in depth and it's more of a confirmation of what we get with the drill rig, the information we've gotten with the drill rig.
All right, the next one is from Paul. When cone penetration testing, is the steel beam inserted in the soil when it is hit for measuring seismic?
It is not inserted in the soil. What we do is we set it on the ground, and then, like in that picture that you have on the screen right there, it's underneath those back jacks of the drill rig. So the weight of the drill rig is holding it onto the ground um, when we actually hit the ends of it.
Here's one from Robert. Does the state or town keep a central record of bore data for others to reference or for general analysis?
Not at this time in New York State that I know of. I do know there is a requirement for water well drillers to submit data, and that's somewhat useful in New York State, but it doesn't give you a lot of soils data. It's more bedrock depths. Internally within ATL, we have more than 50 years experience doing subsurface investigations, and we have our own internal database that we can look at going back based on map locations.
All right, here's one from John. Curious if you created that CPT form or if you could share what company developed it.
That CPT form is coming out of the software. Um, our system is a Vertex system, and they have a couple of different templates that you can output from their software.
And one from Robert. Do clients ever ask for pollutant analysis of water and soil at depths?
Certainly, and that's certainly something we can help with. Generally, when that happens, we get our environmental side involved of our business. The office next to me is our senior environmental engineer, and what'll happen is a lot of times his environmental technicians or engineers will be out with our drill rigs, and they'll take samples of the soils that we collect for different pollutant analysis.
All right, here's one from a different John. How do you convert from non-SPT sampler end value to SPT sample end value?
There's a calculation that's based on the efficiency of the hammer, and that's where I talked about the N60 is what you're referring to, and that's the 60% efficient hammer of the safety hammer. And there's factors you put on it depending on what the efficiency of the hammer is.
All right, and I think we've got time for one more, and this is from Tulkumar. I apologize if I pronounced your name incorrectly. Is there a minimum depth of SB required for commercial building about 30 foot high? Or for a commercial building about 30 foot high?
There's no actual depth requirement in the building code. Generally, we talk about depth. We talk about 20% high, deeper than the building is high. So for a 30-foot tall building, you'd probably want to get to 40 or 50 feet just to make sure. But again, some of that may depend on what the soils are. If we're going to be in real soft soils, we may need to go deeper because you may need to look at alternative foundation systems for that type of a building if you have soft or loose soils.
All righty. And it looks like we're at the end of our time. Thank you so much, Adam. And
Thank you.
thank you to everyone who has participated. Our webinar is now coming to an end.